Let's take a moment to go back through the process that we used last week in lab to work with the Mauna Loa atmospheric CO2 data that started in 1982 and went up through, I think it was 2009. So what we had is starting in 1982, monthly readings of atmospheric CO2 in parts per million. So that's all contained in column D. And then we had established the yearly average in column F. And since that stuff is yearly versus monthly, we have fewer of those readings than of the monthly data. And so the first thing we wanted to do was to develop a linear equation for the data from the yearly averages. So I'm going to click, hold, and drag to select all of that data. And remember, I gave you a shortcut where you can do either Command-Shift down arrow or Control-Shift down arrow for a Mac and PC respectively in order to highlight that quickly. In any case, once you've highlighted it, we're going to go and insert a scatter plot from which we will get a trend line. So I right-click on a point, add a trend line of linear. I want the equation on the chart. And here I don't need the r-squared value, so I'm not going to put that one on. But I close it off, and then when I move my equation, I see that I've got y equals 1.6713x plus 338.67, where here x is going to be time in years, and y is going to be atmospheric CO2 in parts per million. Now, what I wanted to do with that linear trend is subtract it from the monthly data. So in order to do that, I'm going to take each monthly reading and subtract off the predicted value from this linear equation. But I need to modify it so that instead of time being measured in years, it's measured in months. In order to do that, I'm first going to put months since 1982 as a column. And so I start with 0 and then increment by 1. And I'm going to do that all the way to the bottom of the sheet. So I click, hold, and drag. All the way down to 2009. And then I do data minus linear. So like I said, I'm going to take the monthly reading and subtract off the prediction from this line. So the line is going to be, let's see, 1.6713 over 12 to scale for months times time in months, and then plus that 338.67 and hit enter. Yeah, that looks good. Thank you, Excel. And then I double click to put that all the way down for all of my data. And so the idea is that now we should have, instead of the increasing oscillatory trend that we saw before, we should just have the pure oscillations. So to see if that's the case, I'm going to look at just the first 3 years of data, and hopefully we'll have a nice clean looking sinusoidal function. So if I go and now insert a scatter plot, I do have something that looks pretty much like a noisy sine curve. And so here I'm going to put parameters for sine curve, sine model. So I'm going to have my amplitude, the parameter pertaining to the period, that b, which is 2 pi over the period, my horizontal shift, and then my midline. And my estimates here for amplitude. So notice that I go from a max of about 5 to a min of about negative 2.1. So altogether that's like 7.1. If I divide it by 2, I've got roughly 3.5, so I'll just start off there. And notice that the amplitude should be positive. We have, sine starting roughly at its midline and increasing, so it hasn't been flipped. Otherwise, we would put a negative in front of that a parameter. And then for b, we said this should be 2 times pi over the period, which for us should be 12 months. And then horizontal shift, I'll come back to that in a minute. Let's look at the midline. So we said midline should be halfway between the max value of 5 and the min value of roughly -2. So it seems like if we add on our amplitude of 3.5 to -2, we end up with right about positive 1.5. So again, that's just a really rough guess as to what the midline is. And so now we want to see how far we've shifted from the midline when time is 0. And so it looks like there's not a ton of shift because 1.5 is right about here, and it looks like we're starting roughly at that point as well when time is 0. So I'm going to initially guess that the horizontal shift is 0. And again, the solver function is going to clean that up for us in just a minute. So I'm going to get rid of this for the time being. And then I want to do my predicted sine model. And so here I'm going to use parameter a, which is J15, that is fixed, so I'm using my dollar signs, times sine of, use the parameter b, which is $J$16, times the quantity of time, which is here, minus my parameter h $J$17, all plus my midline, which is $J$18. Great. Let's see if it complains at us. No, it gave us something nice. Perfect. All right, so now I'm going to drag that all the way down, and this time it's working a little quicker. So it's always hard to get it just right. So now we've got our predictions based on the parameters that we've established, but we want to look at the squared residuals and then the sum of those and minimize the sum. So first, let's get our squared residuals. So that's going to be the leftover piece that we were fitting the sine curve to. Subtract off the prediction, and then we'll want to square all of that. And I can double click to take that all the way down. And now if I take the sum of all those squared residuals, I should just have all of that data that I'm summing up. And right now it's at 663. Not too bad, but we remember from class that solver can get it even smaller for us. Okay, so let's go ahead and pull up that bad boy, bring up solver. My objective cell is, it's not N, but instead it's going to be M15. I do want to minimize it, and I'm changing the variable cells in column J. And I don't need to mess with constraints right away. If I think that solver isn't giving me a great solution, then I can add some later. But for now, I'll just say, yes, this is a nonlinear equation that I'm using. The sine curve we know is a nonlinear function. And so let's just see what solver can do for us. So I'm going to click solve. And it says it has a solution. Let's keep it and look at it. All right, so now the sum of squared residuals is 503, so that is smaller than before. Our amplitude looks to be about 3. Our value of b is 0.5, which should be right about 2 pi over 12. H was ever so slightly a right shift, which seems reasonable based on that scatter plot that we saw. And then our midline is about 0.9088, blah, blah, blah. So let's now graph our actual data and then add to it the fitted data and just see how that all looks. So we'll do a scatter. Right, I forgot that this looks so ugly when you include all of the data. Let's see if I stretch it out. Does it look better? It looks a little bit better. Okay, so I'm going to add to this other series. So now this is the observed sine part, and now I want predicted sine part, and my y values here are coming from this stuff. So we can look at this, and of course our prediction is perfectly sinusoidal, whereas our observations still do vary a little bit. Like notice through here, they dip down a bit, the blue dots. But in general, our orange stuff matches the blue stuff relatively well. So we can be pretty secure that we've got a decent model at this point. So now, if I look at my total model, that's going to be the predicted linear part, which we said was, oh goodness, what was it? It was the 1.6713 over 12 times some business, plus some business. Oh, let's not do that. All right, so I'm going to copy that in as my linear part, and I am still referencing my month since 1982 as the time portion, and then to that I will add the predicted sine part and take that all the way down. And now let's plot all of the data against all of our predicted data. So let's see, I'm going to grab all of this, insert scatter. Again, I'll want to maybe stretch this out a little bit just to make it easier to see what's going on. To this, I'm going to add our predicted stuff. So this was our observed CO2. And we've got the model CO2, and that's coming from this piece. Click OK, and notice that we do a pretty good job. Right? We only see some blue peeking out here and there, but otherwise our orange stuff matches up pretty well with the blue stuff. So altogether, a super solid model. Good work, Gus. And if we wanted the sum of the squared residuals for everything, well, here I'll do squared residual for total model. Whoops. So that's going to be our observed minus predicted quantity squared all the way down. And then now I'm going to add all of those up. And look what we get here. And so that's not going to be a surprise to many of you because you anticipated that we would get the same thing for the SS res here as we did with our other model. Or maybe this is a surprise, and so if it is, you can think about why this shouldn't be a surprise, especially now that we've seen it, why it makes sense. But in any case, now we can just repeat that whole process with instead of a linear portion for the yearly averages, we can first fit it with a quadratic, subtract that off, fit what remains with a sinusoid, etc., and then do the same thing fitting the linear averages with an exponential model, subtracting that off, and then fitting with a different sinusoid. So do let me know what questions you have as you work through this. But I hope this video is a little bit helpful in reminding you the process that we went through. So please rewatch if necessary, and yeah, let me know what questions you have.